The word mechanics basically is a study of both statics or stationary and dynamics systems. And when we talk about fluid mechanics, we are basically talking about the study of fluid systems that are both moving and stationary, right? So we will touch on both of them. We talked also about hydrodynamics. When we talk, the moment the word hydro comes in, we are basically talking about water. And we are talking about water at low speed. That is to say rivers, dams, and so on. Hydraulics is a subcategory of hydrodynamics, which deals with fluids in pipes and open channels. That is hydraulics. It also, in some ways, it talks about non-Newtonian fluids. We will come down to classification of fluid mechanics, but we will understand that based on the viscosity, there is very heavy fluids and there is light fluids. Hydraulics also might indicate a system that relies on a very viscous fluid. Gas dynamics is the study of gases. If you remember last Monday, we said fluids is classified into gases and liquids. And then we have a single phase, and we have a two-phase, and we have a multi-phase fluids. Depends whether you have a gas and a liquid, or if you have both gas, liquid, and solid in the same system. Aerodynamics is the study of what, guys? Of flying objects, whether it is a rocket, an aeroplane, a drone, or whatever. We are talking about aerodynamics. Metrology, oceanography, and hydrology, this is what we call it environmental fluid mechanics. When we talk about the ocean, when we talk about, have you seen weather? You have seen weather forecast every day. After the news, you will see weather forecast, right? Weather forecast is basically a combination of these: meteorology, oceanography, and hydrology. They will see how the wind is moving and how the ocean will affect them. And then they will tell you, oh, we'll have a rain here and a rain there. Okay. Now, definition of a fluid. This is very fundamental concepts, gentlemen. How do we define a fluid? I think you guys did something in material engineering. I think you did some testing. You have done a tensile test, a compression test, right? And if you talk about solids, let us talk about solids first. If you have a specimen of steel, and if you put it in a tensile test, it will elongate within the elastic limit, and then it will break, right? Within the plastic limit. Have you done such a testing or not yet, guys?
I think not yet, Doctor.
Material science,
yes,
Gentlemen.
Not yet.
We have done it in material
Yes,
science.
Yes, doctor.
Shabab.
Yes, doctor. Yes.
Yes.
Did you do material testing?
Yes, doctor.
Right. So you have an idea about stress strain, right?
Yeah.
Okay. Now, similar to a solid, a fluid is defined in the way that if you look at this, do you see my cursor? Do you see my pointer?
Yes,
Yeah.
doctor.
Shabab,
Yes, doctor, with you.
do you see my pointer? Don't sleep, please.
Yes, Doctor.
Yes, deformed rubber.
Yes, doctor.
Yes, doctor.
Can you see my pointer?
Yes.
Can you see the pointer
Yes,
on the
doctor.
blackboard?
Can't see.
Yes, yes.
Right. So in the same fashion, if you have an element of fluid here, this plate is stationary, and then there is a plate on top which is moving, and you pull this plate with a force, the element of the fluid will deform, similar to the solid. The difference between solids and liquid is that if you continuously apply force, this element of fluid will continue to deform. It will not break. And in a similar fashion to the solids, the force applied on this plate or on this element will create what we call it a shear stress and a shear strain. The shear strain basically as an indication to the degree of deformation. How much the element deform is defined by the shear strain. Be careful about these slides, please. Right? So we have a shear stress tau, which is the force divided by the wetted area. And we have an indication of the degree of deformation, that is the shear strain. Right? So that is a similar form to solids. The only difference between liquids, the way we define liquids. So in brief, you can define as what? You can define a fluid as what? A fluid deforms continuously under the influence of a shear stress, no matter how small it is. In solids, stress is proportional to strain, but in fluid, stress is proportional to strain rate. So we have a strain rate rather than strain. Right? So this is briefly stress and strain is also applied to the fluid. Now, if you focus carefully, if you zoom in a small element here, you will find this force. The force you are applying basically consists of both a tangential and a normal force. If you divide the normal component of the force divided by the area, you will get what we call it a normal stress, and that is the pressure, if you agree. Then the tangential component of the force divided by area will give you what? Will give you shear stress. So there is a normal stress, that is a pressure. So stress is force per unit area, basically. Normal stress is a normal component, which is the pressure. And then the shear stress is the tangential. Pressure is the normal stress, as we said. Zero stress means the fluid is at rest. Zero shear stress, we are dealing with the fluid at rest without any force applied on it. Now, again, in defining liquid and gases, the best way to define them is basically based on the intermolecular level. Okay, in liquids, the intermolecular level between the molecules is much stronger than gas. Therefore, in liquids, groups of molecules can move relative to each other. In gases, a gas expands until it encounters the walls of the container. A better way to visualize solids, liquids, and gases is based on this picture here. So as you can see, the intermolecular forces in solids is very strong. That is why you will see the solid keeping its shape. The intermolecular forces between liquids is generally slightly weak. And therefore, although it does not expand, but it does not keep its shape. If you put water in a glass, it will take the shape of the glass. If you put it in a square container, it will fill the square container. صح يا شباب ولا أنا غلطان؟
صح دكتور.
In gases, no. If you just spray a perfume in a room, eventually at the end of the room you will smell the perfume, right? Why do you smell the perfume? Because the molecular forces between the molecules of gases is very weak, and then it allows them to expand to fill the whole area, no matter how large this area is. So this is the best way to describe solids, liquids, and fluids. Now, a gas and vapor, there is a difference between a gas and vapor. Can anyone tell me what is the difference when we say a gas and when we say a vapor?
Yes, doctor. I can see it. For the vapor, it's a mix between gases and liquids.
That is absolutely correct. The word mixture is the best word that you can describe a vapor. I think you did in solid in thermodynamic one, you did vapors.
Yes.
So a vapor is a mixture. What he said here is a state of condensation. That is to say, there is particles of liquids embedded within the gas. But a gas is a single phase. A vapor is two phase.
Yes.
Macroscopic and classical approaches, and we talked about this. You can look at fluid mechanics from a macro or a micro scale, or from engineering classical concepts, or from a statistical point of view. Application of fluid mechanics, there are many applications, gentlemen. And I think if you look to the industrial area behind you in Jubail University College, you will see a lot of application of fluid mechanics. But this picture shows typical application. For example, this is what? This is a heart, artificial heart. This is a dam. This is what, guys? Cooling towers. This is a ship. This is an aeroplane, aerodynamics. This is a car. Blood in vessels of a human being is all fluid mechanics problems or systems. Okay. This is a factory. These two are factories or water pipelines. And this is wind turbine. All these are what? Are fluid systems. We can all talk about them as what? As fluid systems. Now, we are still continuing with the introduction of basic concepts in fluid mechanics. One of the very basic concepts in fluid mechanics is something called the no-slip condition. What is the no-slip condition? Just, I want you to look at this picture here. This is a plate, a solid surface, right? If I ask a question, the atoms or the molecules of water that is in contact with the surface, how much do you expect? Let us assume the fluid is moving with a velocity 5 meters per second. Far away from the surface, the velocity is what? 5 meters per second. Do you see my writing?
Yes.
Yes.
There is a fluid moving with a 5 meters per second on top of this stationary plate. Right? Now, what my question is, what do you expect the velocity of the molecule that are touching the plate? How much would the velocity be? Can someone answer me?
I think it will be more than 5.
It will be slower, doctor.
Because
Will be decreasing,
when you put a liquid in a surface.
Shabab,
Hello, doctor, can you hear me?
Doctor, you hear me or not?
gentlemen,
Doctor, can you hear me?
don't go and sleep. Or don't log and go and sleep, please. Some people, they will log in and they will go to sleep. No, I can't hear you. I can't hear you, ya Ayad. Ya Mujahid,
Doctor.
can you hear me now? I think I don't have any problem. Can you hear me?
I hear
Yes,
you.
but I can. Yeah, then talk, ya akhi, talk. I want you to talk. I asked a question. I said this is a stationary plate, and then there is a water or whatever fluid moving with 5 meters per second. What would be the velocity of the molecule that are in touch with the plate?
It will be faster, doctor.
It will be very fast, huh?
Yes.
Faster than 5 meters per second.
Yes, faster than 5 meters per second. Because when you put a liquid in a surface, the velocity will increase.
Right. Anyone object on this view of this gentleman, ya shabab? And عندي
Doctor, can you hear me?
Yes, I can hear you, yes.
I think it will be slower on the surface. of the plate.
It will be what?
Slower.
It will be slower. Now, the plate itself is not moving. The plate velocity is 0. How much will be the velocity of the molecule? I will put it. Just take a molecule in touch with this plate here. This molecule, how much will the velocity be?
Maybe 7.
Maybe 7. So this is the one view. The other one said it's lower. How much do you expect it here? The one who said it's lower.
I don't know, but I think it will be slower than before it hits the plate.
I'm not talking before it hits the plate. I'm talking about a particle of this fluid that is in touch with the plate. The plate velocity is 0.
0, doctor.
This is the third one, huh? This is another guy, huh?
Yeah, it will stop.
This is the right view, gentlemen. It will stop. This is the one who put it right. It will stop. He said it will stop. He is absolutely right. Because the plate is stopping, is not moving. Any molecule in touch with the plate, like this molecule, will have a 0 velocity as far as the plate is stationary. And that is what is called, ya shabab, non-slip. Non-slip means what? Slip means what? Slip means able to move. Non-slip, that is unable to move. Any molecule, gentlemen, in touch with a stationary solid surface, the velocity is what, guys? Is 0. Then, moving from the solid surface up, the velocity will start to increase until it reaches the maximum. If the fluid here is 5 meters per second, the velocity here will be 5 meters per second. Now, it will move gradually. Look at this shape here. This is the velocity profile. So it is absolutely 0 at the surface, and then it start increasing gradually. Why is it starting to increase gradually? Because there is something called boundary layer, gentlemen. What is happening here, gentlemen? There is a friction close to the surface. The molecules close to the surface will encounter what we call it a friction, and then a boundary layer will develop. The boundary layer definition is what the flow region adjacent to the wall in which the viscous effects are significant. Viscous is coming from friction, right? So close to the wall, the velocity becomes 0 of the fluid, and a boundary layer develop. Now this boundary layer, through this boundary layer, if you study further fluid mechanics, you will understand there are many sub-layers here. But right now, let us talk about the boundary layer. This boundary layer, the viscous effect, the friction effect, will be significant some distance from the surface until the velocity becomes equal the maximum velocity or the inflow velocity. But within the boundary layer, the velocity will be less than the maximum velocity. And this is what we call it what? No slip boundary condition. It's a very important condition in fluid mechanics. Please pay attention to it. A brief history of fluid mechanics. We are still talking about concepts and definitions. And this is where fluid mechanics started. Where did it start? We will refer to a very prominent engineer, fluid engineer called Reynolds. And Reynolds discovered what we call it Reynolds number, and that was in Manchester, 1975. Reynolds was able to distinguish between different regimes of flow. What I'm saying, regimes means, we will come down to it. When the flow moves very fast, a fluid flow is either laminar, transitional, or turbulent. Let us talk about laminar and turbulent. I think you know about laminar and turbulent, or you have heard about laminar flow and turbulent flow. Laminar flow and turbulent flow are classified based on Reynolds number. and this is the gentleman called Reynolds, who discovers Reynolds number. This is a brief history in fluid mechanics. Now, where did we start aeroplanes? You know Al-Ikhwan Wright brothers, who discovered the first aeroplane and launched it from the sea.
Yes.
Now, eventually, now we have very modern systems like what? Wind turbine and so on. Now, classification of fluid flows. We defined what is a fluid. We defined the boundary conditions called non-slip boundary conditions. Now, this is a very important topic, classification of fluid mechanics. Right? Now, assignment 1, gentlemen. Assignment 1. Are you with me, guys? I'm talking about an assessment here.
Yes, Doctor.
Yes, with you, Doctor.
Yes, Doctor.
Yes.
Assignment 1 will be most likely it will be a presentation where groups of students write, if they are 4, they will write 4 slides, and if they are 5, they will write 5 slides, and they will do some presentation for us. They might talk about some classification of fluid mechanics or classification of fluid flows, right? Now, fluid flows are classified on many categories, and generally speaking, the classification will either rely on a property of a fluid flow or on a geometry of a fluid flow. Now, the first classes of fluid flows we talked about, we will describe them as viscous versus inviscid regions of flow. So we have viscous flows and we have inviscid flows. Now here we will come to define a property called viscosity. Or we have just talked about no slip boundary condition, and we said there is a boundary layer close to the wall. There is a boundary layer, and within this boundary layer, the viscous effect is significant. The friction between the surface and the molecules of the flow of the fluid is high enough to delay the speed. Okay, so this gives us, but if you move far away here, we call it inviscid flow. So this is a viscous flow, and this is inviscid flow. Now, try to distinguish between viscosity, which is a property of the fluid, and between a viscous and non-viscous flows. This is a flow, this is a fluid in movement. Close to the wall, there is a viscous region, and we call it viscous flow. Far away from the surface, there is inviscid flow region. Okay? So this is the first class of fluid flows, viscous versus inviscid flows. We have internal versus external flow. If you have a pipeline, right? If you have a pipeline and the flow go into the pipeline, this is external or internal flow, guys?
Internal. Internal.
Again,
Yes.
Doctor.
If you have a pipeline like this,
Internal, I think that.
this is internal flow.
Internal.
This is an internal flow. But this is a ball, a cylinder in a flow. This is internal or external?
External.
This is external flow. So there is a class of fluid flows called internal or external flows, depending on what? On the geometry. The first is the property. This is a geometry. Okay? Now, compressible versus incompressible. This is, when we talk about compressibility, we are basically talking about the density of the fluid, gentlemen. There are some fluids that the density does not change no matter how much pressure and temperature they are subjected to. But there are fluids, if you press them hard and if you heat them hard, right, the density will change. And therefore we have a compressible and incompressible flow. Now, if you look at this shape here, this is a rocket flying with supersonic speed. Okay, so the air, when it punches the air doesn't feel it very well, and therefore shock waves build. This is compressible flow. The density here is almost changing. Now, based on the speed and the speed of sound, compressible and incompressible flow introduces a number called Mach number, if you have heard about it. Mach number is velocity of the object divided by the speed of sound in that medium. If you are in water, the speed of sound in water. If you are in air, the speed of sound in air. And then Mach number basically classifies the flow, whether it is sonic, supersonic, or hypersonic, or subsonic. Mach number equal 1 sonic, less than 1 subsonic. Mach number greater than 1 supersonic. Mach number much greater than 1 is hypersonic. Okay, so this is compressible and incompressible fluid flows. We have laminar versus turbulent flows. And we have just talked about Reynolds number and Reynolds, the engineer Reynolds. Okay, so we have a laminar flow. Even in the morning, when you open the tap very slowly, the water is slow as one bulk. The water moves from the tap as one bulk, if you have noticed. But if you open the bulk, the tap fully, water will scatter everywhere. And that's the turbulent flow. In between laminar flow and turbulent flow, there is a transitional flow. So in scientific way, the way we describe laminar flow, highly ordered fluid motion, characterized by smooth layers of fluid. The flow of highly viscous fluids such as oil at low velocities is typically a laminar flow. Turbulent, a flow that alternates between, turbulent is the highly disordered fluid motion. That is three-dimensional, random, typically occurs at high velocity and is characterized by velocity fluctuations. The flow of low viscosity fluids such as air at high velocities is typically turbulent. So this is a classification of laminar and turbulent. Reynolds number, will come later on to understand that. Reynolds number will tell us whether the flow is laminar, turbulent, or transitional. Okay. Another classification of flow is natural versus forced flow. And I think when you come to do your experimental thermofluid lab, there is an experiment about natural and forced convection. What do we mean by natural and forced convection or forced flows? Okay, talk about a river. Talk about a river.
The river, doctor, will be natural because there is no force or no.
That is correct.
Yeah.
That's absolutely correct. But talk about in Jubail we have marafiq, right? And marafiq has water in big barrels, in big tanks. Have you seen them?
Yes.
And then from there they have pumps, right?
Mm.
They use the pumps to force the water to go into Jubail city. That is what kind of flow? Natural or forced flow?
Force, doctor, of
That
course.
is forced flow. So you understand what the meaning between natural and forced flow. A force, basically, there is you introduce some external force to force the fluid to move. Okay, so this is natural and forced flow. Steady versus unsteady. Now, when we talk about steady, guys, we are talking about the change of velocity and other parameters with time. Right? If the velocity changes with time, let us assume you have a pipe flow. Let us assume you have a pipe flow. Okay? And then you put a velocity meter at this point. And then you started measuring the velocity here at different times. If the velocity at all times becomes constant, then that is a steady flow. If the velocity changes, that is unsteady flow. So steady or unsteady relies on the variation of different parameters, not only the velocity, gentlemen. You have velocity, pressure, and energy. Any fluid flow is characterized by velocity, pressure, and energy. So the term steady, as you can see here, what he says, the term steady implies no change at a point with time. So based on this category, we have steady, unsteady, uniform. We have a uniform flow. The uniform means what? No change with location. That is to say, if you measure here, if you measure here, if you measure here, the velocity is the same. We have periodic. Periodic refers to a kind of unsteady flow in which the flow oscillates between steady, about steady mean, right? So usually, gentlemen, when we analyze fluid flow, we assume it is a steady flow. But what I want you to understand, the word steady means changing with time or not changing with time. 1, 2, and 3-dimensional flows. This is still classification of fluid flows. Okay? This is still classification of fluid flows. Usually, gentlemen, usually we live in how many dimensions, guys? X, Y, and what, guys?
And Z, Doctor.
And Z. There is a 4th dimension. What is it, guys? There is a 4th dimension. Do you know what is the 4th dimension? Any system, guys, even yourself, you are sitting at home now, you live in 4 dimensions, not 3 dimensions. Yes, if you look to the room is X, Y, and Z, but there is another dimension. What is it?
Time, Doctor.
Time. Brilliant. Thank you. The 4th dimension is time, gentlemen. Okay, but let us talk about X, Y, and Z. A fluid flow can be 3-dimensional, but sometimes we say, okay, the variation along the Z is not very significant, and we can ignore the Z direction and we talk about 2-dimension only. We can describe the fluid flow as an XY system only. But we can also go extreme and say, okay, the variation along the Y is not important, and then the flow becomes what? 1-dimensional along the stream Y's, the X direction. But generally speaking, guys, any fluid flow is 3-dimensional. Not 3-dimensional, it's 4th dimensional. Because the time comes in and then it characterizes the fluid either steady or unsteady. Okay? So here he's trying to tell us some logical example. This is a bullet flying, and the bullet is symmetrical. And his question is, do you think this fluid is 2-dimensional or 3-dimensional? His arguments, since the flow since the bullet is symmetrical, the variation along the Z is negligible. And therefore the fluid is what, guys? Is 2-dimensional rather than 3-dimensional. Okay? Look at it from logical. There is no calculation here. This is just a logical argumentation. Look at it from logical point of view. Now, we are still introducing, guys, basic concepts. And I think you have seen this in your thermofluid 1, thermodynamic 1. Systems and control volume. If you want to analyze any system, you have to build a control volume. The control volume has to contain all the material within the system. صح ولا ما صح؟ شباب انتم معي ولا ننتم؟
Right.
Right. And then when we talk about, so we have talked about a system, it is surroundings, it is boundaries. And then we have 2 thermodynamic systems. We have a closed system and we have an open system. Yes, talk.
Yes, for the closed system, there is no mass will change.
There is no mass will change. There is no mass will to cross the boundary.
Yes, and for the
That's closed system.
open system, there is a steady and non-steady.
No. Steady and non-steady is different category. But let us say in an open system, the mass can cross the boundary. In a closed system, only energy can cross the boundary. The mass does not have a chance to cross the boundary. But in an open system, both mass and energy can cross the boundary. That is the main difference. Therefore, kinetic energy belongs to an open system, but it does not belong to a closed system because there is no movement. There is no movement unless the system expand. Unless the piston expand, like, okay, this is the closed system, right? If you inject energy here, it will give you some work. That is the first law of thermodynamic, and it will store some of the energy inside, internal energy. But generally speaking, in an open system like a turbine or a compressor, look at this system here. This is a closed system, but this is an open system. Okay, so an open system, a fluid comes from here and leaves from there. So it comes with the velocity and leaves with the velocity. So the kinetic energy is relevant. But a closed system like that, it does not have movement. There is no kinetic energy. Are we together, gentlemen?
Yes.
So open system
Yes,
and control system. Right? تفضل. You want to talk? Do you want to say something? Okay. Dimensions, يا شباب. Importance of dimensions and units. I think all of you, first of all, we are going to stick to the metric system only, gentlemen. We are not going to go to the British system. But it is also essential for you to understand the conversion between metric and British system, because when you go to if you work in one of these industrial areas, you will get some quantities specification in British systems. So rather than getting stuck not knowing what to do with a pound and a ton, you would better understand them now, right? So dimensions and units, please differentiate between them. There is basic dimensions like mass, length, time. We abbreviate them by what? M, L, and T. Temperature, capital T. These we call them primary or fundamental dimensions. Others like velocity, energy, volume, these are expressed in terms of primary dimensions and are called what? Secondary dimensions or derived dimension, because velocity, energy, or volume is coming as a result of a physical phenomenon. It's not something constant. Now we know metric and we know English systems, gentlemen. If you look at this table here, for example, length, this is the dimension L, capital L. The unit is what, guys? Is meter. The mass, abbreviated by capital M. The unit is what, guys? Kilogram. Time, unit is what? Second, and so on. Temperature, degrees Kelvin. Current, amps. Light, candela. Matter, mole. Okay. Now you know this here. Kilo is 10 to the power 3, mega, giga, and tera. Are you familiar with these units, gentlemen, or standards?
Yes, sir.
Right. Moving further, some SI and English units. Conversion factors. You can see the conversion factor between bound force, right? You can see pound meter, right? The work and how to change from Newton to joule, calories, and BTU. Although we are not gonna use them in the exam, but it is this slide, in my opinion, is very important if you want to change from British to English system. You see the pound, it starts from the pound and kilogram, the meter and feet. How to change from kilogram into pound meter, and how to change from feet into meter, and so on. Okay, all these are talking about units. Gravity, we know the gravity 9.81, right? So this is a metric system and this is a British system. So 9.81 we use here at 32.174, that's the gravity. Okay, energy, we are talking about what? We're talking about energy here, gentlemen, right? Dimensional homogeneity. What do you mean by dimensional homogeneity? He said all equations must be dimensionally homogeneous. Right. Can you add, for example, can you add pressure plus force? Can you add pressure plus force, guys?
No, Doctor.
No, because they are not homogeneous. Pressure is totally different property than force, but you can add force plus force. You can add pressure plus pressure. That is what we mean by what? By dimensionally homogeneous equation. If an equation contains more than one term, all these terms must be having the same units, the same meaning. Energy, 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 pressure, 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 force, force, force. You cannot add energy plus pressure plus force. You cannot do that because that is an inhomogeneous equation. Okay? Again, these are just conversion unit between metric and British systems. Okay? All we are talking about conversion between metric and British system. Please note them down. We will always focus on problems using metric system, but that does not mean we should ignore the British system, gentlemen. Because as I said, practically, if you become an engineer, you will meet both of them. Okay? Now, here is a simple example, gentlemen, to tell us about units, the importance of units, and how to understand and how to put a homogeneous calculations. Let us read it, please. Focus with me. School is paying this figure. Can someone read for me this figure, please? Can you read it for me? A school is paying what?
$0.09 per kilowatt hour.
لا. No. You see here is the units. You see here is how to read the units. I want someone to read for me this thing here. How can you pronounce it, please? How can you read it? This figure.
0.09 dollars per kilowatt an hour.
No, close, but no.
9 cents per kilowatt an hour.
No, I think the first one who mentioned. Again, repeat the gentleman who just said before this guy. You said what?
I say $0.9 per kilowatt an hour.
Per kilowatt hour.
Yes.
Yes. $0.09 per kilowatt hour. يعني سعر الكيلووات hour $0.09. So you read it this way. $0.09 per kilowatt hour. That is to say, the price of this electricity is for each kilowatt hour, the price is how much? $0.09. So school is paying $0.09 per kilowatt hour for electrical power. To reduce its power bill, the school installs a wind turbine. This is the wind turbine, which with a rated power of 30 kilowatt. listen, this is a rated power, 30 kilowatt. If the turbine operates 2,200 hours per year at the rated power, which is 30 kilowatt, determine the amount of electrical power generated by the wind turbine and the money saved. You see, the example is simple, it's straightforward, but it tells you a lot about the units, how to combine different units. Now, the school bought this wind turbine, which is rated at 30 kilowatt hour. The wind turbine operates 2,200 hours per year. If you multiply 30 kilowatt by 2,200 hours, it will give you what, guys? It will give you kilowatt hour. صح ولا ما صح?
صح.
Yes.
It gives you kilowatt hour. Right? If you multiply the kilowatt hour by the price, it will give you what, guys? If you multiply, okay, you have kilowatt hour, you have kilowatt hour. If you multiply by this pound per kilowatt hour, what will it give you, guys?
Pound.
It will give you pound or dollar, sorry, pound or dollar, whatever. It will give you the dollar, صح ولا ما صح? Because kilowatt hour will disappear with the kilowatt hour. It will give you the dollars. You see the units, how the units can be combined. Units, gentlemen, I have been teaching this course for a while now, and many mistakes of the students comes in the unit. Sometimes you give them units in centimeter and meter. In one problem, they will not differentiate between a centimeter and a meter. They will just go ahead and calculate. They will take it as one unit, and that's it. So please pay attention. So the problem is straightforward. The wind turbine is rated 30 kilowatt. If you multiply by 2,200 hours, that will give you the total kilowatt hour it will produce per year. If you multiply by the price here, which is dollar per kilowatt hour, it will give you how much dollars it will generate. That is 5,940. That is to say, this school will be able to save $5,940 per year out of its electrical consumption, because the electric will come from the wind turbine. Okay? Now, moving forward, there is another example here to show you how to distinguish between units. It says a tank, read with me please, a tank is filled with oil whose density is 850 kilogram per meter cube. If the volume of the tank is 2 meter cube, determine the amount of the mass. So mass is in kilogram, right, ya shabab, or not?
Yes, Doctor.
Yes.
And if you are given the volume, and the density, how will you get the mass?
Multiply.
Multiply them.
Multiply, yeah. But be careful. Look at the units. The density is kilogram per what? Per meter cube.
Yes.
And the volume is what? Meter cube. So the volume will go with the volume. We will get what, guys?
Kilogram.
Kilogram. Straightforward. So the two examples we have seen here is just reflection to how to manipulate the units. Please pay attention to the units. Right. The last section, or the section before the last section in this chapter, is mathematical modeling of engineering problems. This section is very important, to be very honest with you guys, when you do your final year project. Right? Basically, it tells you if you have a physical problem, if you have an engineering problem, how will you solve it? What kind of parameters, what kind of steps should you undertake in order to solve an engineering problem facing you? Right. Generally speaking, we have two approaches. We have an experimental approach, and we have what, guys? an analytical approach. Experimental approach is straightforward. You build a prototype. You have a car, you are designing a car, you want to understand the aerodynamic of the car. You build a small model of the car exactly typical to the car in reality. You put it in a wind tunnel and then you run the wind tunnel. The wind tunnel will tell you how the flow is distributed around the car. But running an experiment, gentlemen, is very, very expensive. It is time consuming, it is labor consuming. Even when you get the data, analyzing the data is time consuming. Therefore, most people go for what? Analytical approach. That is mathematical approach. That is to say, building a mathematical model. Building a mathematical model for what? For the system or for the problem. So how will you model it mathematically? There are few steps, gentlemen, you have to follow. First of all, define, we call it problem statement. We call it what, guys? Problem statement. What is your problem? Let us say our problem is to optimize the aerodynamic of a car. Some students are developing a new generation of Formula One cars, and they want to optimize the aerodynamic performance of this Formula One car. That is a physical problem. What is the second step should you take? Guys, I'm going to continue and I'm going to leave you. I'm not going to continue up to 9 o'clock. So, but I'm supposed to give you 10 minutes break, but I will continue and I will give you more time at the end, okay? Are we in agreement?
Yes, Doctor, no problem.
Yes,
Okay.
better. That's
Better. So you first of all, we said in order to develop a mathematical model for a problem, we consider the physical problem statement. The second step you should consider is what kind of variables affect the performance of the physical problem. Pressure, temperature, speed, volume, weight. You have to identify all the variables that are associated with the performance of the system. Third step, what would you do? Reasonable assumptions and approximation, because, gentlemen, the more variable you have here, the more complex the problem would be to analyze. Some variables will be significant, others are insignificant. So those variables which do not have a lot of influence on the system, you have to what? Ignore them. This is what we call it assumptions and approximations. Third step, apply relevant physical laws. PV equal, or force is equal what? MA. This is a physical law. صح ولا مصح? Force is equal mass time acceleration. Come and see what kind of physical laws are associated with this system and put all of them. When you put all these physical laws, what will happen is you come out with what? A differential equation, not necessarily differential equation, but you will come out with a mathematical model for the problem. Now, the mathematical model might be easy to solve on a piece of paper, but might be needing what? To develop some sort of codes, apply application solution techniques. So you develop a code, a MATLAB or a MATLAB, or go to more complex softwares and develop what, guys? A solution technique. Apply boundary conditions. If you remember, we have been talking about the no-slip condition. What kind of boundary condition? What are the surroundings of the problem? You have to apply all of them. You have to take them into consideration because this physical system will operate under specific boundary conditions. Therefore, each single boundary conditions that surround the physical problem, you have to take it into consideration and you have to reflect it in this mathematical model here. Then solve. If you do all this, solve the problem. You will get a good solution. Tell us something. So here is telling you there is there is a complex versus simple model. For example, look at this. This is what, guys?
Helicopter.
This is a helicopter, right? Helicopter is a very complex. This gentleman here, someone gave the task of modeling this helicopter to a student, and then the student modeled it just as an elliptic shape. He just looked at it like that, and he just put an elliptic shape, and that is the model for this helicopter. Do you think he's reasonable or not reasonable?
Not reasonable. Doctor.
Not reasonable, because it is very, very simple. He's ignoring a lot of features from the frame and the shape itself. More serious issues. So these are the steps we have just been talking about, right? So basically, your model, you have to model it in a reasonable way. You put a reasonable model, right? And then solve. There is a simple way to reach, and there is a very difficult way. It absolutely depends on what kind of assumptions and what kind of solution method you are going to adopt. Okay. Now, this is he's telling you an example, gentlemen. Example of mistaken model developed. What do you see here, gentlemen? What do you see in this car and this car? This is a big SUV car, right? Like this is an SUV car like a Jims, right? And this is like a Lexus.
Yes.
Now this gentleman modeled the drag force. He modeled the drag force in this car and in this car. This is a streamlined version of this car. That's what you can see. And then look at this arrow here. The arrow basically indicates the magnitude of the FD, which is a dynamic force drag. His model showed that the drag force for the SUV is much, much smaller, if you look at it carefully, than this Lexus or streamlined car. Is this right or wrong?
Wrong.
Very wrong. Because logically, this car, which is streamlined, and this bulk car, this car should have much, much smaller aerodynamic force compared to this one. Therefore, gentlemen, when you develop a problem, you have to apply reasoning. It doesn't mean that you follow these steps here. These are 7 steps. This is important to you when you do your final year project. Okay? When you do these steps, you have to look at the results. When you get the results, you have to look at the results. If the results are correct, fair enough. If not correct, if the results are logical, fair enough. Correct or incorrect, you can only run an experiment. Mathematical model will never tell you whether your results is 110% correct. But you can see they are logical or not. So you have to apply some sort of what? Of logics. Now, fortunately, gentlemen, there is engineering software packages available for you in Jubail University College. Okay, there is MATLAB. Have you studied MATLAB?
No, doctor.
Did you
no,
do
yes.
MATLAB,
No.
guys?
Yes, doctor.
I think
Shabab.
still. Doctor.
Can you hear me?
No,
Not yet, doctor. We not MATLAB.
Did you do C++?
Yes, we do it.
Yes, we did, teacher.
I didn't.
C++ is a coding language. You can write a code in C++ to solve very complex equations. But there is something called engineering equation solver. We don't have it in Jubail University College. But engineering equation solver, you can write any code using what? Using C++ to solve any engineering problem. What we have That's what he's trying to tell you here. There is these kind of equations, for example, right? If you have been asked to solve this equation, this can be easy to solve on a piece of paper. But very complex equation, you cannot solve them in a piece of paper. So you have to write a code. You have to use your knowledge in C++ and write a code, okay, to solve them. We have softwares. We have FlowLab. We don't have FlowLab. FlowLab contain, he's just putting it as a title, but there is computational fluid dynamics codes, ANSYS and Fluent. We have both ANSYS and Fluent, guys, in our labs. You have what? You have both ANSYS and Fluent in our labs. So these can help you basically solve any engineering problems, and I really encourage you to learn ANSYS. Accuracy and precision, guys. Accuracy and precision is how much digits should you consider. Now there is all these are digits. You can know about them. There is no problem. There is an example here which will tell us how important the units are. Let us read this problem and follow me closely, please. Right. It says Jennifer is conducting an experiment that uses cooling water from a garden hose. In order to calculate the volume flow rate of water through the hose, she times how long it takes to fill the container. The volume of water collected is 1.1 gallon. Gallon is a British unit, guys. In time, 45.6 seconds. She collected how much, guys? 1.1 gallon in how many seconds? In 45.62. Measured by stopwatch. Calculate the volume flow rate through the hose in units of cubic meters per minute. Right. So it is 1.1 gallon in how many minutes, guys? In how many seconds? 45 point what? 0.62. This is gallon per second. صح?
Yes.
Right. The gallon is equal 3.785 if you multiply by 3.78. It will give you liter. And if you change it into meter, you have to multiply by 10. You have to divide by what? 1,000, صح? That is meter per second. The gallon, 1.1 gallon, if you multiply by 3.785, you change it into liters. Because the gallon is a British unit, and the gallon has 3.785 liter. Now, in order to change the liter into meter cube, you have to divide by what? By 1,000 or multiply by 10 to minus 3. Now, this is meter per second. صح ولا ما صح يا شباب?
Yes.
This is meter per second. Do you agree with me? Hello, gentlemen. This is a very important point.
Yes, Doctor, can you hear me?
Yes, I am.
Yes.
How much? Someone has a calculator or his mobile near him. How much is this? So multiply 1.19 by 3.78, divide by 1,000, and divide by 45.62. How much is it? Oh.
Yes.
Oh. Huh?
9.8 multiplied by 10 to the power minus 5.
Minus 5. 9.8. So 0.00098, صح?
Yes.
طيب, if I ask you to write the answer into 2 digits, for 2 digits, what will you get?
9.8 multiplied by 10 to the power minus 5.
I said, right, that is correct. If I write it, it is 0.000098, صح? I'm writing it here. Do you see my casa? So it is 0.000098, صح يا شباب? Are you following me, gentlemen?
Yes.
Yes, Doctor.
If I ask you to write your answer to 2 digits, accuracy 2 digits, what will you get?
Approximately 9.9.
ركز يا ابني, ركز. Just focus a little bit, please.
0.98 multiplied by 10 power
يا
minus
شباب,
3.
the answer is 9.8 times 10 raised to the power 5, صح?
Yes.
So this is point 0.00098, صح?
Yeah.
Shall I write it like that?
No.
غلطان أنا, I'm wrong?
It's correct, but like it's too long.
يا أخي, mister, you said the answer is 9.8 times 10 raised to the power
Yes,
5,
yes,
صح?
that's correct.
صح? Did you say that or I'm wrong?
Yes.
So 9.8 times 10 raised to the power 5 can be written like this.
Mm-hmm.
يا شباب, في 30 شخص جوا. Are you in agreement with me or not?
Yes.
Yes. Yes.
طيب, if I ask you to write the answer into 2 digits, what will you get?
0.
يا شباب, انتوا صحيين ولا ما صحيين؟ This is 0.000098. If I want to read it for 2 digits only, what will I get?
9.8.
لا إله إلا الله محمد رسول الله. يا شباب,
0.1.
I'm not asking a very complex question. I have 0.000098. If I want to write this in 2 digits only, what will I get?
10 power minus 4.
0.98.
والله يا جماعة حيرتوني اليوم. يا شباب خلينا أحكي بالعربي. 0.00098. أنا لو قلت لكم اكتبوها 2 digits, approximate, write for 2 digits only.
0.
Which digits will you take?
1.
اخوانا 2 digits يعني هنا يا شباب. شوفوا 2 digits هنا, صح ولا ما صح؟
هنا
3 digits وين؟ هنا.
بعد
4 digits وين؟ هنا, صح؟
ايوه.
5 digits is here. So 2 digits, it gives me what?
0.98.
لا حول ولا قوة.
0. Doctor. 0.
0.00.
It gives you 0 يا شباب.
I said 0 before, Doctor, but you didn't hear me.
I don't know, I'm probably. It gives you 0. 2 digits, it gives you 0. 3 digits, it gives you what, guys? 0.
1.
0.
0. Yes, 4 digits 0.
4 digits 0.
4 digits 1.
Well, if you approximate it. But up to 3 digits, you are getting 0, صح يا شباب? The answer
Yes.
is 0.
Yes.
But is it physically 0?
No.
No.
No. Here is the importance of the digits. Here is the importance of the digits, يا شباب. So be careful. You have to take your answer to as long as necessary. Because specific example, if we take it for the first digits, it is 0. Actually, the problem is this lady has collected water, صح ولا ما صح?
Yes.
This lady has collected water. So the answer is physical, is there is something, there is water. Right? Can you hear me? I see a problem in the internet. Can you hear me, gentlemen?
Yes, doctor.
Hello?
Yes, Doctor.
Can you hear me?
Yes.
Okay, the problem has. Now, okay. So this is, guys, what is importance of digits. Please pay attention to it. In summary, gentlemen, this is chapter 1. We passed through many things, the no-slip boundary condition. We talked about brief history of fluid mechanics. Of a very important point is classification of fluid flow. This might be the subject of your, when we cover chapter 2, you have to write assignment 1. Some of you might talk about one of these classification. Okay? We talked about systems and control. We talked about dimensions and unit. We talked about mathematical modeling and problem solving and engineering softwares. And we talked about how accuracy and precision is necessary. This is chapter 1. Thank you very much for listening. Any questions, gentlemen?
Thank you, doctor.
Thank you,
Thank
teacher.
you, Doctor.
Thank you.
Thank you, Doctor. Thank you.
ايوه يا شباب، لو في اي واحد عنده سؤال please let us stop recording.